Setting alarm limits on vibration spectra, monitoring signals to ensure system safety and reliability. Purpose of setting alarm limits. Setting alarm limits is a foundational activity in any professional vibration-based condition monitoring or predictive maintenance program. Modern plants collect enormous volumes of vibration data on a routine basis, including overall vibration levels, spectra, waveforms, and specialized measurements such as bearing condition indicators. Without alarm limits, this data has little practical value because engineers and analysts cannot efficiently determine which machines require attention. Correctly configured alarm limits allow software systems to automatically screen incoming data and generate exception reports, highlighting only those assets that deviate from expected behavior. This approach dramatically reduces analysis workload, improves response time, and ensures that developing faults are not overlooked. From an engineering perspective, alarm limits are not intended to provide diagnosis on their own. Instead, they act as a decision support mechanism that triggers deeper investigation when predefined thresholds are exceeded. Poorly set alarms can be just as harmful as having no alarms at all. Overly sensitive limits lead to frequent false alarms, causing alarm fatigue and loss of confidence in the monitoring system. Conversely, limits that are set too high may fail to detect faults until catastrophic failure is imminent. Therefore, understanding how and why alarm limits are established is essential for reliability engineers, vibration analysts, and maintenance professionals who aim to balance early fault detection with practical, actionable results. Understanding vibration data behavior, change versus absolute vibration levels. One of the most important principles in vibration analysis is that absolute vibration amplitude, by itself, often has limited meaning. The vibration measured at a bearing housing or machine casing is not a direct measurement of the internal forces acting on the machine. Instead, it is the structural response of the machine, influenced by mass, stiffness, damping, mounting conditions, and foundation design. As a result, two identical machines operating under different loads or mounted on different foundations may exhibit very different vibration amplitudes while both are healthy. Because of this variability, condition monitoring programs focus primarily on change over time rather than absolute values. Establishing baseline measurements when a machine is known to be in good condition provides a reference point against which future data can be compared. Trending vibration parameters allows engineers to identify gradual degradation, sudden changes, or abnormal growth patterns that indicate developing faults such as imbalance, misalignment, looseness, or bearing damage. Alarm limits are therefore most effective when they are linked to deviations from normal behavior rather than arbitrary vibration numbers. This philosophy underpins both calculated alarms and many spectrum-based alarm strategies, reinforcing the idea that stability and repeatability are just as important as the measured amplitude itself. Using ISO standards as a starting point. International standards provide widely accepted guidelines for evaluating machine vibration and are often used as an initial reference when setting alarm limits. ISO 10816 focuses on vibration measured on bearing housings using accelerometers or velocity probes and defines vibration severity in terms of RMS velocity over a specified frequency range. ISO 7919, on the other hand, applies to shaft vibration measured with proximity probes and is commonly used on large rotating machinery such as turbines and compressors. These standards categorize machines by size, type, and mounting conditions and define zones that represent acceptable, tolerable, or unacceptable vibration levels. While ISO standards are valuable for benchmarking and for starting new monitoring programs, they have inherent limitations. They are based on generalized machine classifications and do not account for plant-specific factors such as unique operating conditions, structural resonances, or historical machine behavior. For this reason, experienced engineers treat ISO limits as guidance rather than strict pass-fail criteria. In practice, ISO-based alarms are often used initially and later refined or replaced with calculated limits derived from actual machine data as the monitoring program matures. Why overall values are not sufficient. Overall RMS vibration is a convenient single-value metric and is useful for high-level trending and screening. However, it has significant limitations when used as the primary alarm criterion. Overall values are typically dominated by the largest vibration component, often the running speed, one-order, frequency. This dominance can mask smaller but critical components such as bearing defect frequencies or gear mesh sidebands. As a result, a machine may experience severe localized damage while the overall vibration remains relatively unchanged. Additionally, overall RMS measurements average vibration energy across a wide frequency range, reducing sensitivity to early-stage faults that manifest at specific frequencies. From an engineering standpoint, relying solely on overall alarms increases the risk of late detection and limits diagnostic capability. This realization has driven the adoption of spectrum-based alarms, which examine selected frequency regions or the entire spectrum in greater detail. Overall vibration alarms still play an important role, but they should be complemented by more targeted alarm strategies to ensure comprehensive fault detection. Concept of spectrum alarming. Spectrum-based alarming extends beyond single overall values by analyzing vibration amplitude within specific frequency regions or across the entire frequency range. This approach aligns more closely with how faults develop and manifest in rotating machinery. Different mechanical problems generate vibration at characteristic frequencies, such as unbalance at running speed, misalignment at harmonics of running speed, and bearing defects at calculated bearing frequencies. By applying alarm limits to these spectral components, engineers can detect faults earlier and with greater confidence. Spectrum alarms can be implemented using band alarms or mask, envelope, alarms, depending on software capability and analysis philosophy. Both methods aim to automatically identify abnormal spectral behavior while reducing the need for manual review of every spectrum. When properly configured, spectrum-based alarms significantly enhance the effectiveness of exception reporting and allow analysts to focus their expertise where it is most needed. Principles of band alarming. Band alarms operate by dividing the vibration spectrum into predefined frequency bands, each associated with a particular machine behavior or fault mechanism. Common examples include bands around running speed, one-order, harmonics, subsynchronous frequencies, vane pass frequencies, or broader ranges covering multiple orders. Within each band, the software extracts a representative value, such as peak amplitude, RMS value, or total energy, and compares it against an alarm threshold. If the threshold is exceeded, an alarm is triggered. Band alarms offer flexibility, as different limits can be applied to different frequency regions based on their expected behavior and criticality. They also allow alarms to be labeled meaningfully, such as unbalance or vane pass, which improves the clarity of exception reports. From an engineering perspective, band alarms strike a balance between sensitivity and interpretability, making them a popular choice in many industrial monitoring systems. Using band values for condition trending. In addition to alarming, band alarms provide valuable data for long-term condition trending. Each band produces a numerical value that can be trended over time, allowing engineers to observe gradual increases, cyclical behavior, or sudden changes in specific frequency regions. This capability is particularly useful for monitoring fault progression and estimating remaining useful life. Trending band values helps distinguish between stable machines and those experiencing accelerating degradation. It also supports maintenance planning by providing objective evidence of deterioration rather than relying solely on threshold exceedance. From a reliability engineering standpoint, the dual use of band alarms for both alarming and trending maximizes the return on investment in vibration monitoring systems. It reinforces proactive maintenance practices by enabling data-driven decisions rather than reactive responses to failures. Understanding mask alarm concepts. Mask alarms, also known as envelope alarms in the context of spectrum alarming, apply an alarm boundary across the entire vibration spectrum rather than dividing it into discrete bands. The alarm limit follows the general shape of the baseline spectrum, with allowable increases defined at each frequency. This approach ensures that all frequencies are monitored, including those not explicitly anticipated during alarm setup. Mask alarms can be more sensitive to unexpected or emerging faults that fall outside predefined bands. However, they may provide less immediate diagnostic clarity because an alarm indicates that a frequency has exceeded the mask without inherently identifying the fault type. Some systems enhance mask alarms by correlating exceeded frequencies with known forcing frequencies such as running speed or vane pass. From an engineering perspective, mask alarms offer comprehensive coverage but often require greater experience and understanding to interpret effectively. Fixed versus calculated alarm approaches. Alarm limits can be established manually or through automated calculation based on historical data. Manual alarms typically rely on standards, published charts, or engineering judgment and are often used when a monitoring program is first implemented. Calculated alarms, by contrast, are derived from baseline measurements and statistical analysis of previous data. These alarms are tailored to the specific machine and operating conditions, making them more sensitive to meaningful change. A common rule of thumb is that a significant problem may exist when vibration levels increase by approximately 50% from baseline, while a doubling of vibration often indicates a serious condition. Calculated alarms require sufficient historical data and stable operating conditions to be effective. Best practice in professional programs is to begin with fixed alarms to get started, then transition to calculated alarms as data history grows and confidence in machine behavior improves. Avoiding false alarms and missed faults. Effective alarm management requires continuous refinement and engineering judgment. Alarm limits should be reviewed and adjusted as machines are repaired, operating conditions change, or additional data becomes available. Exception reports should consistently highlight a manageable number of machines. If too many assets appear in alarm, the limits are likely too sensitive. Conversely, a lack of alarms over long periods may indicate overly conservative thresholds. Engineers must also ensure that alarms drive action. An alarm that is repeatedly ignored loses its value and undermines confidence in the monitoring system. By combining standards-based guidance, machine-specific calculated limits, spectrum-based techniques, and disciplined review processes, organizations can build alarm systems that provide timely, credible, and actionable information. This approach supports the ultimate goal of condition monitoring, improving reliability, reducing unplanned downtime, and optimizing maintenance resources.